My name's Brian Oliver, and it's a standard disclaimer which says everything you see here doesn't exist. It does exist, it doesn't exist. We all have to have these. So today we're going to talk about sharding middleware, and as we often hear about sharding databases. Now we're going to talk a little about applying some of those concepts and how they apply to middleware. And what we're trying to achieve with those things. So I said I'm Brian Oliver. I've mainly work in the coherence team. I'm sort of a solutions architect at large. Go around to other teams telling them about sharding and scaling. This is Cameron Purdy. Can you introduce yourself?
I'm hoping these slides are good because I haven't seen them.
So I wrote these slides, and I've been working with Cameron for many, many years. And I deliberately didn't give them to him. It's really good to watch Cameron work and see him on his feet. So if anyone saw the Java 1 keynote on Sunday, he was pretty good on his feet. So we're going to do that again.
As long as nobody calls me fat this time.
Yeah. Yeah, they did call you fat in front of where's your fuel band? 2,000 people. So a lot of these concepts we're talking about actually, I think, I don't know if Cameron invented them, but I was certainly influenced from working with Cameron for probably the last 8 years on these things. And we've been applying these principles over and over again. And they're a part of, products like Coherence, which is where I work. And Cameron's a founding creator of Coherence. And we wanted to try and uplift that and talk a little bit about how we apply these, not just to applications, but how we're starting to investigate applying these to just middleware in general and how that fits with Oracle. And of course we're on a mad drive, as everyone probably knows, to move to cloud. So there's a whole range of sort of paradigms here that are starting to stitch together, and we want to sort of step back a little bit and talk about how you get to cloud and some of the challenges to get to cloud. So let's get going. So far so good?
So far so good.
We'll get you at the whiteboard in a minute. So we'll do it in this order. We're going to talk a little bit about cloud, what it means to be cloud ready, what cloud providers give us, and then let's drill in and we'll talk about code and things that you should do or shouldn't do when you're writing code if you want to move towards cloud. And we're not just talking about you, we're actually talking about what we do as well, how we think about middleware and how we're starting to think about middleware and the principles we apply. Then we're going to talk about sharding, and I guess the sort of real examples will come when we're basically going to workshop a few architectures, and it's going to be interactive, so you can feel free to yell out. So we're going to try and whiteboard as much as we can. So not death by slides. So let's just set the scene a little bit. I just went to Wikipedia and went, okay, define cloud for me, and it comes up with a whole bunch of stuff. So provisioning agility, starting and stopping stuff quickly, pretty easy. You must be able to sort of reduce operation and capital costs. It's interesting, it doesn't say anything about development cost. Nowhere have I said, let's reduce development costs. It's all about the other side. So we're going to talk a bit about the cost in terms of development. Device location independence, we sort of know about that. Virtualization, so we know about cloud, we want to virtualize a lot of stuff. And once you start virtualizing, we talk about multi-tenancy, and multi-tenancy is very difficult. At the sort of server tier virtualization, you can sort of do it, and I think Cameron will maybe provide some insight into this. How do you virtualize and have multiple tenants inside a JVM so they don't run into each other and starve each other of threads and resources? We can talk about that. The notion of reliability. How does reliability affect when you move to cloud? Most of the times when you talk about reliability, what they say is, you can have 2 sites. You can have multiple sites. Okay. I'm not quite sure if that covers what we need to do as developers, and so on. We can go down the list. So typical cloud provider, and we can pick anyone: Rackspace, Amazon. This is basically the sort of stuff you get. Now, what is sort of interesting is that, well, let's go on. There are different types of, so that's sort of infrastructure providers. This is sort of application. Other cloud providers and sort of Oracle would sit in here as like virtual machine as a service, social integration, app logging, security. You know, the first set of slides we're really talking about, you know, infrastructure as a service.
So is that PowerPoint you're running?
Yes.
It's PowerPoint. What address is it loaded at in RAM?
Don't know. Do I care?
How many threads does it use?
Don't know. Anyone want to guess? How many threads does PowerPoint use? A lot, probably.
50. How many cores do you have?
Don't know.
You don't know how many cores you have, but it's working.
Yeah. I think I have 4. No, I might have 2. Actually, I have 2 in this. It's an old Mac.
You know, I remember years ago, before we had threads, we actually had to like know exactly what was running where because we actually had to put it there. Like if you had 2 CPUs in an SMP box, you actually had to like preboot the chip and actually link on your code to actually get executed.
So what you're saying here is we don't care so much.
I think we're in the stone age with the cloud right now. I think in some ways we're kind of in the stone age with middleware in that like how many servers does your app run on? You know, and I see someone in the audience who's probably heard me talk about this before. Like, for the most part, you shouldn't care. Like, how many CPUs do you have? How many threads do you have? How many kilobytes? What's a kilobyte? Like, I mean, if it's a Java app, how many gigabytes are you? like you shouldn't care, right? But when it comes to new areas of technology, like we haven't gotten there yet, right? We haven't pushed those concerns down into the operating system, right? So if we say, well, how are you going to shard an application so that it scales across multiple machines? Like it's still a conscious thought. But if we said, how are you going to thread shard your app server Java EE app so it'll use more than one core? Like, so if you ask someone that, they look at you like, what, are you an idiot? Like, you just do this and, requests come in, they get load balanced and, goes to different threads. I think there's a thread pool or something. How many threads? I don't know. I think it's dynamic. It tunes itself. Doesn't it tune itself? I think you helped write some of that.
So when you actually look at what you're offered, it's basically a virtual data center. We haven't progressed. Like,
here's a box, but it's not a box.
It's a box. It's not a box. It's somewhere you don't know where it is. So we've got the don't know where it is part, but it's still the same stuff. And so there are higher levels. So some of the cloud providers are starting to provide other levels, but it's still like you have to understand it. You have to like allocate, know where this stuff is. And really to take advantage of it, you almost have to change the way you write your code.
And one of the things I think we want to accomplish with concepts like partitioning or sharding in Java EE is that if you're talking about it in 5 years, we failed, right? If you still have to think about it consciously, like how do I partition up work? How do I split this up so it'll scale? Like part of the goal has to be how do we push things down just like you would into an operating system, right? I don't think about dynamic linking if I'm writing executables for Windows, even though I know behind the scenes it does all that, right? It's creating lots of junky little code snippets for me behind the scenes just so when I call foo, it calls into the actual DL. Like, why would I want to know that?
Yeah.
And if I'm running something on a scale-out elastic infrastructure, why would I want to know how it's being divided or how many servers it happens to be running on a particular time?
So you can see, like, working with this guy, this is what I listen to all the time. But one of the passionate visions here is like this point here. Like, we want developers using the stuff that we're working on, including like the commercial stuff, but also like the community stuff, part of Java, that you don't have to think about this stuff. Less and less.
I've got a question in the third row. So the question is, if you're using the cloud, should you have an ops team, or you don't even need an ops team?
Yeah. At the moment, you absolutely have to have an ops team. If you move to one of the sort of infrastructure as a service, you have to have it. Or,
if you remember the
what
original,
happens, the developers become the ops team.
the original Java 2EE, J2EE as it's called back in '99, I guess. This idea was that you would put these components in place, and then the server that hosted them would provide a container for them that would allow multi-threaded, multi-core, multi-SMP environments to spread the load over it. And you didn't have to, when you wrote a servlet, actually, I'm going to lie a little bit because I remember you did actually have to think about it at first. If you remember that, there was an interface you could tag onto a servlet to say, make me a new one for every thread or something, some hack like that. But other than that, you didn't have to think about it at all. Like you'd write a servlet, and you don't care how many instances there are or how many threads there are. And with a program, that's what a programming model gives you. It says that someone spent the time to think through up front, what questions you have to answer. So in the servlet case, what question do you have to answer? Somebody here has written a servlet. There's only one question you have to answer. Service.
Yep,
Thank you.
On service, do service.
Right? You can also implement a init if you want. I think there's a method called init and things like that. So you could do lifecycle stuff on top of it. But basically, question comes in. It's service. I have a request and a response. Do something. Take something from there, put something in there.
You don't need to know what port it's running on.
You don't need to know what port it's running on? No. What IP address? But actually, there's a lot of that information available. You could drill down and get that if you needed it. And I think that's the same thing we have to think about. How are we going to build middleware, elastic environments for the cloud? And think about what we're trying to accomplish. How many were here yesterday when I spoke? Was it yesterday I spoke here? How many?
Monday.
Anybody? Monday? Couple? I mean, it's that concept of S plus HA. How do I get scalability and high availability baked into everything I do? So what we're trying to do with our middleware, with Java EE design, with the products that we build on top of that, is think about how do we push it into the programming contract. So it's like service, right? Request, response, service. You answer this question and you'll get scalability of your servlets. Well, same thing here.
Do you find it somewhat ironic? I don't know if it's ironic that we went through this phase of having containers which are providing all these facilities to containers being semi-evil and very evil to coming back now to virtualization is container. And we're actually talking about having more and more containment to provide these facilities.
Well, in Java EE, the reason the concept of container was denigrated, hated for some period of time wasn't the container concept itself. It was the fact that to get anything to run in the container, you had to write a dissertation of XML, cut and paste your code 7 times into interfaces and abstract classes, and then run a pre-compilation process that took 5 minutes, and then restart a server that took 8 minutes, only to find out you mistyped something.
So there's an enormous gap between sort of what we're being provided. Like if we look at what the cloud infrastructure is like, and what that list of abilities and things that we have to achieve, it's a phenomenally large gap. And what I found was particularly scary in just having a customer. I haven't told you about this. I had a customer call last week, and they were like desperate. We got a new CTO, a huge company. We have a new CTO, and we're told we have to move all of our stuff out of our data center to 2 separate cloud instances with HA in 2 weeks. Right? And it's like, okay. And they're like, they know their CTO's mad, like insane. But there is this total gap. And so how as developers do we start? And Oracle's actively researching and thinking about what we can do to move forward. So, I don't know how to answer that. We're working on it, but it won't be ready in 2 weeks.
I guess that's a different form of a 2-week notice.
That's 2 week notice, yeah. So this is a fundamental disconnect. Okay, and if you're an architect, we've got a lot to do. So we have to deliver these things, and we could sort of let's take out a few of them and let's talk a little bit about them. We only have an hour. So, okay. So let's think about our code. If we want provisioning agility, what do we need to do? What do we have to do? how would you write your application if you want, provisioning agility?
So what do you mean by provisioning agility?
I need to be able to start this thing and stop it. Now, it may not be a whole application. Maybe I want
a service
or a component in an application that's faulty. I need to take that out and upgrade it. Perhaps roll it back.
Well, I think one of the first things I always think about is how to build something in such a way that it operates in the same predictable manner, whether I'm running it on a single server or running it on 100 servers. And one of the key principles for this, and this doesn't necessarily apply to an application as a whole, but it applies to whatever level that you consider to be a service or a component, or maybe it is the entire application. But for that unit, it has to work in a predictable manner, regardless of how elastic it is, whether it's hard-coded to run on one server, hard-coded to run on 10, or it varies, or whatever. And I think rule number one is that responsibility gravitates to the server. In other words, if I have one server, all responsibility gravitates to that one server. So if I start up one server, it's responsible for everything. It's responsible for every aspect of the service. If there's something that happens every once a minute to check some backlog of something or to refresh a cache or something, that server is responsible for it. On the other hand, if I get to 100 servers, I may still, out of that 100 servers, only have one server responsible for a particular task. There may be a task that can only be done by one server. So I have to have a way within that 100 server architecture to make sure that only one server will do it, and if that server dies, that someone else will definitely pick it up, and still there will be exactly one server doing that.
So in terms of, let's move on. In terms of device and location independence, we had this interesting conversation. If I'm going to write an application that has to be deployed to a cloud and has to move around, what are the sort of things am I not or shouldn't I be allowed to do?
Well, that's, and I think you're going to start seeing some of this show up, certainly in our own products as well as in Java EE, what we're doing with CDI all over the place. I would like to get to the point where you never say new. And you certainly never have a static method or use a static instance of something, a singleton instance. Because basically you, as a developer, if you want to build something that can move from one machine to another, or you can't make any assumptions about the environment you're in. And what CDI gives us, what injection gives us, is the ability to just say, look, I know I need something. And I know I could write a line of code that would give it to me and it would work, on my notebook, maybe on a single server. But I abdicate my responsibility for knowing what it is I'm looking for. I'll defer that to the environment that I'm running within.
So declaratively say, this is what I need, instead of saying, in our case, cache factory.get, static factory.get something.
Exactly.
Because, when you think about it this way, if you have a component that's dependent on a static inside a JVM, it's very hard to move that component.
And you just screwed yourself if you want to go to OSGI, for example.
Totally. So as soon as you start using statics, you're going down a path, or you're already in a path.
But think about some of the things that are implicit statics as well. When I say new file, new java.io.file, that's a static. You don't see it because you're newing some object. You're thinking, well, I know there's a /tmp well, it's not going to work on Windows, but I'm going to say new file. But it's a static because there's a file system implied by saying new file. But if I say inject a file into me, I need a file. I need to read and write from something, right? Now in the injection, I can say, I need you to inject for me a temporary file. Okay, temporary file, that's no problem, because I could have a local drive on my server. Or maybe there are no drives on my servers because I redeploy to a new data center and they have a policy that everything goes on the SAN, so I don't have a local file. So I can create a memory-mapped, memory-based file system, or I can use a SAN, a portion of the SAN that's allocated as temporary storage. But, in other words, instead of assuming that you know something about your environment, because where it gets really pernicious is when that new file is something that has to stick around for a while. You say new file, and this is why Java EE has a prohibition, actually, from using going directly after the file system. So that for things like this, for all the types of resources that you can be consuming, they need to be injected. They should never be grabbed, if you will.
You immediately create a dependency between
an implicit dependency, even worse, embedded in the code
to the file system, to the structure of a file system.
Yeah.
So you can imagine if your application has to be injected with some file, it means that your application doesn't necessarily have to know where it is. You can configure where that is. And you can have, through CDI, you can say, oh, look, it has to be injected. And if it's not there, the application can't run or the component doesn't run. So imagine what happens, changes how you code, because in your code you write new file, if file exists, blah, blah, blah. You have all this error checking around your stuff, just binding yourself to the resources as much as you implicitly. It's the old way of doing it, but imagine you take a new file and you have to be injected with your files or injected with where you can get a group of files or resources. World changes a little bit. Your code changes.
The other thing it does is it causes a configuration reach around because the decisions have to be made from that. That was probably not the most politically correct thing to say. From that place that's grabbing that file, right? So if you need to change how that works, it's down in the code, right? So it's like, oh, I'm going to make this more flexible. So how do you make it more flexible? Well, I'm going to go check system.properties or, and suddenly you get into a giant hairball, and the hairball is like way down there, but then it has to like reach out to find, what its dynamic behavior should be. Where with something like an injection style approach, you just abdicate all that responsibility. You say, this thing will need something.
And right? I don't care where it comes from.
I don't care where it comes from. So now I can mock it more easily. I can, so which makes it much more unit testable. It also makes it friendly whether it's running on one server or 100, whether it's virtualized or not, whether it's...
So I have two other related issues. Am I allowed to create threads? And secondly, am I allowed to open sockets?
Again, they're resources. You should not, as a developer...
But I want to do something asynchronously.
Well, what are the platform services for doing something asynchronously? If you need some platform service, just declare it. Say, inject me with something that I can call back to do something asynchronous with.
So, I don't know, is anyone using Apple? Like this, there's not many Apple notebooks around. What did they do in the last, how many months ago it was, or a year ago? They introduced what infrastructure into the operating system? Grand Central, yeah, GCD, Grand Central Dispatch. Take away all of that threading nonsense that you had to write. Like, we have executor service,
yep.
But obviously, like, we need something, and then that helps with multi-tenant, right? So if I have multiple tenants, you don't want to. You want to be inside a JVM, and then each tenant's just like creating their own threads, creating their own files. You want the infrastructure to be able to manage that. And
we used to often do it with JMS, and we'd create some complex patterns of sending messages to maybe a message-driven bean or something like that. But it's interesting that what JMS gave you in that case was actually two things. It gave you that asynchronous nature, but it also made. I talk about software as kind of like energy. You've got kinetic energy and potential energy, right? So if you have a boulder sitting at the top of the hill, it's potential energy, right? And when it starts rolling, it's kinetic energy, right? And one of the problems that you have with highly available systems is that boulder's rolling, and then the server loses the power, and the boulder's not only not rolling, it ceases to exist, right? So what JMS gave you was the boulder's persistence, right? So, another server would be responsible until that JMS message was committed in terms of the consummation of it. Until that transaction is committed, that boulder is still sitting at the top of the hill somewhere, right? So even if it's rolling, until you say, yep, I'm done with that, that potential energy remains. And this is a pattern that's extremely useful for building highly available systems, is that you have to turn what you want to do into data, into information that says, I want to do this. That's the potential energy. And then the converse, or the other half of it, is that you need something like a message-driven bean, or like, we were talking, I need one server out of 100 to be doing something specific. You need someone that's actually looking for that work to be done, executing on it, like as if you will, an executor service. So
a few other things about cloud reliability, and this is obviously everyone understands this. Like going multi-site, just because you deploy multi-site doesn't mean you're suddenly highly available. It's like, okay. So multiple data centers. So you can, DR, and it's like, oh, look, it's very easy, in cloud infrastructure to say, oh, look, I'm going to run up several instances of my app. But
availability zones, for example, on EC2.
Yeah, so the question is like, do you even know? Well, I mean, currently it's basically you deploy your app multiple times. It's like, okay, I've got a center here or a center in New York and a center in London and a center in Dublin. Then you just deploy your apps to those places, and then you configure the load balancing yourself. So it's just as if you had built data centers and you're doing all that work.
To some extent, you have some control over it. So the only one I have experience with on this is EC2. And basically, if you don't say anything, you have no idea they could all be on the same piece of hardware, which is fairly likely to be a single point of failure.
Yeah.
But you can explicitly say, I want these on different servers. I want these in different what they call availability zones, for example. And you can even force them to be in different regions. And basically, every time you tell Amazon something that you want, you just hear ka-ching, ka-ching.
Yeah. So they do give you free traffic between the data centers. Between availability zones. Yeah. Not between the regions.
Not between the regions. Interesting.
So, as we... so you although you can do these deployments, it doesn't really help you. Like you have to be able to design components that they can move and they can work in a cooperative way. And we'll talk a little bit more with the sharding stuff. Obviously, Elasticity, I can start instances and shut them down, but it's fine to do that. But how do I actually move stuff? We were talking about if you have statics and your files are on a local file system, now I have to make sure there's file system replication if I've bound to that. So there's a lot of effort going into it. So I have this slide, and I sort of think there's this scale, right? So resource coupling, and that's sort of what Cameron's talking about. It's this notion of coupling yourself, your program, your application to the resources that you have on that single machine. The more tightly you're coupled to your machine or your deployment, the less likely you will be able to deploy it and scale it and achieve some of those cloud things. But on that side, if you're really tightly coupled, the applications tend to be high performance because they're not going to traverse networks. So there's this spectrum. And on the right, if you have something entirely loosely coupled, and we've seen this paradigm. The actor pattern is a classic example. It's very sort of academic design, lots and lots of messages are passing between them, and there's nothing new about this. Object-oriented programming is all about this. But deployed like that, yep, completely loose coupled. You can move things around, but incredibly chatty. Right, on basically probably the second slowest piece of infrastructure apart from disk. So separating every object potentially with network isn't going to be a great solution. So, some applications work very well like that. So somewhere between those two is some sort of balance, and we have to strike that balance. So we talked a little about this. So being cloud ready means becoming sort of loosely coupled, but we've got to strike this balance. So let's talk a bit about sharding. So one of the things we try to do with sharding or petitioning is to strike a balance, because we want to be able to sort of partition up data, and we always talk about data. We think of services as data, and sort of the way it is across multiple servers and order-preserving manner. And this is actually taken from the MongoDB. Order-preserving is actually quite important when it comes to requests coming into some shard, some petition. Now, you hear about this in a lot in databases. It's principally done to horizontally scale. So a very simple example is I'm just going to take parts of a data set. I'm going to put A to C surnames on a particular set of servers, and then D to F on another set of servers, and And we've been doing this for a long time, and we would manually allocate and associate, tightly couple those shards, those partitions down to individual servers. Essentially that's sort of what MongoDB does.
And there's nothing wrong with that architecture either.
Absolutely not.
I mean, the New York Stock Exchange uses that architecture for their trading engines.
Yep.
They have a pair of servers for each
shard.
And it's predefined. There's not a lot of new ticker symbols every day on the equity exchanges.
The data stays. The amount of data, things that you can trade, stays very static. Yep. Even a few thousand added or removed a day is pretty static for them.
Yep.
So, sharding.
Looking at the dictionary, it means a broken piece of glass.
Yes. Right. So there's
actually on the site Quora.com, there's actually a discussion of what's the history of the word sharding. The first time I heard it was back in a conversation with Gregor Hopi, who at the time was at Google, and he said that the reason they used the word sharding was just because they liked it, but they really meant partitioning. So,
right. and basically it says sharding is the petitioning. So we should just say petitioning of data services. But I used sharding because it sounded cooler. Sorry. But you see this throughout most databases. If you look up sort of sharding technology or sharding patterns, it's just going to be databases. So, but it's applying like those principles into middleware.
As soon as you shard a database, you lose everything you want to use database for. You get scale, but you lose facility, you lose the query across shard.
Yeah, as long it becomes basically you can't do a lot of operations across the entire database because now there's lots of little parts. It becomes harder to do things across the entire data set. But within a data set, it's better, and you can have finer granularity. So there's good and bad with sharding. But in principle, we want to apply it to any sort of state. We want to apply it to state. I think it's really important. It's not necessarily that simple. Sharding is hard. So the question is, like, how do you shard? Like, do we shard based on region? Do you shard, okay, we'll have East Coast stuff, an East Coast data center, we'll have West Coast and we'll have Mid Coast. Okay, and then have all the infrastructure designed like that. And you design your whole app, every part of your tier, the data center, everything this way. So what happens if you make a mistake in your choice of sharding strategy? You're sort of hosed a little bit. And this is off some F5 slides. So they're talking about different techniques. Now, obviously, F5 is interested in switching technology between these shards. But
that's what's called global load balancing, which is another word for DNS.
So MongoDB does sort of sharding as well. It's like lots of little MongoDBs, some configuration, and you can go to one Mongo, and it will point you and route you to the appropriate shard, and off you go. And if you don't have to do joins, which key value store, no SQL, and don't really necessarily need to do that, then it's never a problem. There are some challenges with this architecture, though. It basically has to keep an index of where everything is in all the shards, which itself is data, which itself could be large, which you should actually shard as well. So it becomes a little challenging. So I'm going to get Cameron to do some talking, and I want to ask him some questions. So we're going to talk about what goes in a shard, what's associated with shards, how many shards should there be if you're building a system? How many should you have? Is one? What is the number that you should have? Should you be able to add and remove them? What sort of technique do you use to associate them with physical infrastructure? Can you do it dynamically? What's the granularity of them? Where are they stored? What sort of
that's a lot of questions.
Yeah, we're gonna do it through an example though, and strategies for resilience. So you can take the stand. So I want Cameron to. This is his test. I want Cameron to walk through like breaking down something like Nike. Nike Plus. So like they got around like 20 million runners for all sports people, and they, like Cameron, he uses his band, and they have 20 million people. I'm making up the number; it's around that. Who log in and want to upload their sports results, jumping results, running results into a system that has to stay running all the time. How do you go about solving that?
That's the only thing I get?
That's what you get. So you could do it. I mean, we could say, how could we? Well, what would be a traditional way? We could take a whole bunch of stateless servers. We could stick all the data in a database, and we could just smash the database with requests.
Oh, actually,
now we
that's
know
actually
that
how they
doesn't-
built it the first time.
Yeah, so we know that doesn't work.
Yes. On 8/8/8, so August 8th, 2008, they had they were going for 1 million concurrent runners. This was the end of the Beijing Olympics, and they had a massive overload on their systems, and that's when they started to re-architect. My understanding is that's when they started to re-architect for the new system that Nike Plus uses. But one of the first interesting things you start to learn when you look at a system is what things are throwaway and what things aren't. Right? That's the first thing you try to understand. What things have to be consistent, what things don't matter. And the reason I always try to start sorting into these buckets is that the only thing you pay for in scaling is consistency. Everything else scales infinitely. If you don't need consistency,
Hello World scales awesomely.
Google scales is great because it doesn't have to be consistent. If I do the query twice on Google, I get 2 different answers because it's not running off a shared database. There's not like some database in the back, Wizard of Oz back in the back, like, okay, you're looking for that. Yep, it's on HTTP. But like, there's no one lookup, right? There's the information is completely out of sync across thousands of servers. Well, not completely. They try to get it in sync, but they don't care if it is or isn't.
So does anyone ever raise a support request with Google if you do the same search twice and get different results? Does anyone really care? Do you understand why they have the I feel lucky button? Right? It's like, this is the I really don't care. Just show me something.
And then there's other information that they also don't care if it's consistent, like advertising stuff, right? Yeah. They want to make a quick guess, really quick. What should I throw up here for an advertisement on this query? What should I show them on Gmail if they're looking at their mail? What advertisement should I show them? They don't have to have like the absolute transactionally consistent, but not only that, the things that you would think are incredibly important to have like high quality as a service, like charging for ads. Like, it's a nickel an ad. Who cares if you accidentally lose one, right? So, like a nickel. Who cares if you lose a nickel? So you have to like challenge the assumptions of what the qualities of service are that you want. Because what you're trying to do in architecture is you're trying to push back each area of functionality to its actual set of required qualities of service. So for example, if I don't have to be transactionally consistent on, the number of dollars being charged for ads, I can asynchronously store that information. Asynchronous is fine because if I lose a server, I lose a couple nickels, right? Even if the customer says, don't charge me more than this budget, this is my budget amount. Well, if I have more to charge them than that, I just take a loss, I eat the overflow, right? So
the cost of architecting a perfect architecture is way greater.
That's right. And asynchronous architecture is architecture that scales way better than synchronous architecture. So if I can make it asynchronous in terms of data updates, and if I can relax consistency in terms of data access, I can scale infinitely, near infinitely.
So sharding lets you do a bunch of things asynchronously.
Like what?
Well, instead of having all of your customers queued up coming into one system, you can break them up into buckets. We used to call them buckets, right? We used to actually call the shards buckets inside of Coherence. So you can break them up into buckets, and they can all work independently. There's probably some ordering within that bucket. It's a fundamental principle. Okay, so I've got all of these customers. What are my shards going to be?
Well, the interesting thing with the Nike one is that they can't fit all the data in memory.
Right.
So that's like problem number one. Like they want to run real fast, like everything's in memory, but it's more data than fits in memory. And it's not a question of cost. I mean, there's just much more data than there is RAM. So how to deal with this? Well, you go running and you come back and you sync your band, right? The thing is, you come back and you sync your band, like you're there. But while you were out running, you weren't connected. You weren't, well, maybe you were. I guess they have apps on the phones and stuff now too. But like when you're not connected, that system doesn't have to do anything in relation to you.
So if your user is a shard, like we talked about granularity, if your user is a shard, that shard doesn't actually have to exist in the system, in the live system.
In the live system, in the live set. And then, but what it does is it introduces another concept that becomes very handy in this type of system, which is an event-driven system. Like when the user logs in, that's a pretty good hint that that user is going to start doing things that the system, to answer those requests, will need information about that user. Right? So like a login is an event. And it's an event that a system can use to prefetch asynchronously, for example, start to prefetch all the information that's likely to be needed on behalf of that user. So it's as if you have all the information in memory, because a login takes 10 milliseconds. But from the user's point of view, it takes 100 to get there and back. And then they're looking at the screen. It actually takes us time. We're kind of slow as people to like actually read the screen and click on whatever it is we're wanting to do.
So I have two questions then. What would be in the user shard, and where would that shard be located? So I'm in Amazon and I have lots of servers.
Well, the first thing is after you push back on consistency requirements, after you push back on synchronicity requirements, then you start to think about how you're going to collect things together, right? So in this case, in the Nike Plus case, all of the I don't actually know their system in and out. I mean, I did some whiteboarding sessions, runs. But on a system like that, or a system like an e-commerce system, all the information related to a user, that's the information that they need very, very fast response times for. So basically, what you want to do is you want to start to co-locate things, bundle them around the user. So whatever the user information, anything related to it, what do we call it? The affinity. We call it affinity and coherence. It's this idea that, yes, I have a user, and then I have orders. I have some way, for example, maybe it's a shopping cart or maybe it's orders or something like that. I want that information to gravitate to the user so that when I go to do something, answer some question about the user, and I send the request to where that information would be in a distributed environment, that all the other information it needs is actually going to be either there or close by there, or, assuming it's not there, it'll know how to get it.
It's going to come out together. Right. So, I'll have to yell. So you can imagine a way not to do this. If Mikey did have lots and lots of servers, and your user shard is here. This is the Cameron Purdy shard, and the request comes in from outside because you're plugging your band, you upload your run. Probably the first thing he wants to see is, as he's uploading, previous runs. Right. Has anyone used Nike Plus? So you want to see your previous runs, right? Because I've just done a run, I'm going to compare them, and I'm going to see it's a very cool site. So where would I not store my previous runs? Wouldn't store it over here.
Right.
This is my first run. This is my second run.
You'd create affinity between the state that you're processing, and you'd also, it's not just the state. You also create affinity for the requests themselves. So the requests hone in, if you will, on the part of the system that manages that information. It could be database. It's architecture. It's That's correct.
So yeah,
I wish you had John's slide. Do you remember the one he had the 4 elements of scalability?
Right. So you can do some things. I know, we've done some work in this area, but yeah, your database is here, and from your load balancer, you can actually direct them to the server where the data would be.
But even if you don't,
right. Once you get load balances, and then the requests keep going to that server, but it picks a server based on the load balancing algorithm.
Right, but you can actually plug in load balancing. First of all, you can plug in load balancing algorithms. The other thing that most people start with, at least, is a 2-phase. So what we called, on the first one, we call it spraying. So what I'll call stateless load balancing, meaning the request comes in, no matter The balancer doesn't even look at the request. It's just like, go there, 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 whatever, random, round robin. And so that comes down to the first tier of servers. Typically, those are web servers, Apache with a plugin like Mod Proxy or something like that. And then that set of servers actually now takes the time to look at the HTTP header and figure out what server it should go to. So and by doing this, basically you completely unload the F5, which is getting hit by every single incoming request. So it has nothing to do except send it on.
And then directing from your front end through maybe middleware down to a specific instance of a database.
So from the web server, it goes down to a specific instance of the next tier, whatever that is, app server.
You're setting your data. Maybe you've got 2 locations. Your data in one server in here and one in your whatever.
Right. And at this point, like, let's say we don't even...
The one with Europe, though, is actually a completely different use case. That's what they were talking about with the pluggable routing. That's called global load balancing. So global load balancing is a great story because it took me a while to figure out how it worked because no one published any documents on it. And there's a reason why. The dirty secret of global load balancing is it's called DNS. And DNS is free, and they wanted... So at the time, around the year 2000, you had a couple of different companies, including Big IP and F5. A couple, Cisco bought one of them. And anyway, you had these companies making tons of money on load balancing hardware, and basically embedded stuff for doing load balancing. And they wanted to be able to load balance between data centers. And so you would come in and you'd come into a data center, and it would give you an IP address as basically as a redirect, if you will, using DNS. And they wanted to sell this, but they didn't want to call it DNS because it's free. So instead they called it global load balancing. And so here, this is where you would actually plug in some logic so that when it comes in, it would know based on who's coming in or whatever to send them somewhere else. And you can often see this, if you do NS lookups and turn your caching off, you can see this company like Yahoo or Google, it's not like one address, and it's not static either.
But if you don't want to have Cameron Purdy in every single database, then you do have to have something very intelligent.
Yes, so that's called routing, correct.
Okay, but what part of your code is deciding that?
Well, do you want to answer that?
Good point.
So, well, you had some slides in here showing, some of the other.
Let's just think about middleware. Let's not worry so much about the database. So there's a few ways. So I'll talk at the mic. So we won't worry about the database because we don't know what it is. The database. Actually, if we went back to the Mongo one. Mongo actually has a set of config servers. It's basically index. So a request comes in, it goes to that, finds the index for your data, and then routes you back. That's one strategy. Coherence actually does something slightly different.
Another one would be something like memcached.
Memcached.
Right? So memcached, you give it a static list of IP addresses. It hashes whatever it is you're looking for, modulos it by the number of items in that list, and that's the address to go to.
Always. And if that server's down, it's not there.
If it sounds easy, it's not surprising since they wrote it in a weekend.
Yeah. Right, that will get you to that piece of data. Yep. That's right.
So the question here was, again?
Doesn't it rely on uniform distribution of the users to be load balanced correctly?
The question is, doesn't it rely on uniform distribution to be load balanced?
Right. So one of the challenges with, when you look at sharding in the database world, is this challenge of how do you balance the number of users that are in each shard. So there's that problem, but let's say they were all balanced. Let's say you did have balanced shards. How do you allocate those in a way that they're distributed evenly across the servers? But that's still not enough because I could have non-uniform requests for users in a shard.
Yeah, great
so even if I have completely perfect shard allocation, the volume of requests could actually change the dynamic.
Broker-dealers in financial services. So We have a couple cases where someone's built an application, it spreads everything out uniformly, and it's like everything's perfect, except one of their customers is my grandmother, who comes in twice a year, and she's like, okay, my balance looks okay, good. And another customer is like Charles Schwab, with 600,000 customers of their own or something like that. Like so all coming in, like, so you have like one server doing nothing and another server running red hot at 100%. And so again, that's a type of example where distribution doesn't always mean the same thing in terms of uniformity. Is it uniformity of users per machine, or is it uniformity of load, or uniformity of information capacity? What's the target?
So one way I like to think about it.
Don't you have you said you were going to show a movie.
Oh yeah, I do have a movie.
That'd be a cool
one.
one.
One way I think about this is like, okay, let's say in the Nike case, I have had infinite amount of hardware and data center and infinite amount of money. I could basically give every single person who's a customer, 20 odd million of them, their own computer. Right? They have dedicated CPU, dedicated memory. And we back it up and we do it. And so we just take out Amazon. We're just like, we're going to take all your computers. We have awesome quality of service. Or we could try to fit it all on one computer. Somewhere in between is a balance, right? And that involves money and air conditioning and all sorts of things. So the concept of shard is I may have like 20 million shards, but how do I allocate them, or what is the process of allocating them to the hardware is another problem. And you can round robin them. The notion of being able to move them. So when we go back to the beginning, like we were talking about, what are you allowed to do? Your shards shouldn't be statics. Your shards shouldn't be creating files. Your shards, right? I need to alleviate stuff that my shards do, the resources I have them attached to, so I can move them around. So I do have a system, and I add another server, I can balance the shards out.
Is there audio on that, by the way?
No.
No audio?
We're going to make it up as we go.
Sure.
So we've been doing research in this area for a long time. And this is some research. It's a movie that came as we've been looking at shard, we call it petition, allocation strategies.
So this was done by Sun Labs.
And
we still call them Sun Labs sometimes.
Yeah. Oracle/Sun Labs. So this is actually demonstrating a little bit of coherence, and we have one server here, and what we're going to do, there's a couple of services running inside. This is basically a JVM. We're actually going to start up some more JVMs in a second. And so our cluster, so you imagine this in a cloud, so I've added another server, and it's actually, the left is showing the allocation or the server coming up. And at this point, I might just pause it. So at this point, these blue things that just came in, those blue things are what we call like primary shards. So they hold data or data that represents services, and the green ones are backups, because we want to make sure our shards have a backup. So if I lose a server, I can bring it back up and recover the shard. So, and at the top here we say, theoretically or logically, there are unowned ones that haven't been allocated to servers yet. And these are the green ones that are backups. So you can see in this demo, like they all come in, and as new servers arrive, this is actually real time. There are actually servers coming out real time, and we start to move the shards around. And we wanted to visualize how this happened in real time in the system. So there's no outage, like with Amazon. Like they add new stuff all the time. There's no outage. They can move things about.
And they're showing you here as they mouse over which partitions are where for each backup where the primary is, or for each primary where the backup is.
So each server, and Cameron alluded to this, like each server has a responsibility, and they have to look after, in this case, a certain set of active shards and backup shards. And as the mouse moves over, as the pointer moved over, it drew a line between where the primary was and where the backup was, because you want to make sure all the primaries and backups are on different servers. Okay, now we're just doing this in a really small example, but if you imagine applying sharding to a Nike with 20 million customers, and They don't have 20 million shards. There's some number. They've worked out some number. And it's actually pretty easy. The mathematics of it is fairly straightforward to work out what a suitable number would be. It's nice because they can add servers on the fly. This is, right, remember we talked about elasticity? This is what we want, right? We want to add server on the fly or remove servers on the fly. So
the interesting question, though, is what if you only have one server? So go back all the way. Go back all the way to the beginning here. So we start out, we start up the one server. Go ahead, let it play. And you see that as the first server comes up, basically everything goes there. So what is that everything? Right? It's responsibility. Like, if I'm the only one here and something has to get done, I can't give it to someone else to do. That's the model. So a shard isn't a piece of data. It's not a service. It's a responsibility. It could be data. It could be services. It says that, if ownership of a shard is here, that means I'm responsible for whatever's associated with that. If it could be a specific piece of user information. It could be a background process that has to run. So this is how you make sure, whether you have one server or 100 servers, if there's a, if you will, singleton process that has to be executing, you assign it to a shard. You assign it some identity that's uniquely owned somewhere within that environment, so that no matter how many servers you have, only one of them is doing that work.
So let's do it the opposite way. I'm building an application, I write it, runs inside a JVM, then I decide to scale it. You go through this process of basically sharding your architecture afterwards. The degenerate, sort of a degenerate case, a single server case is no real different from a two server case. It's just that a single server is holding all the shards. You start thinking about shards early or immediately, and when you're deploying with a single server, you're just running on your laptop, you still have all of those shards. They're just running in the one JVM. And when I have two JVMs, we just spread them out. And that's absolute key to go to cloud. Like,
whenever you add a server, you need to redistribute the load, right? You need to redistribute the shards.
right. So we're not
Potentially, yes.
What happens if you have 100 gigabytes of data in one server, and you have like 15 or 16 servers, then you add another server, so you have to move potentially 100 gigabytes data from all the machines to one single machine. That takes time.
right.
How do you handle that?
So we have these.
But you don't have to move. First of all, you don't have to move it all at once. It can be completely asynchronous.
Yeah.
So this is showing it moving very fast because they were running on 40 gigabit InfiniBand. That's cheating.
Yeah. So we can move a lot very quickly.
But we could also plug in something here that would, for example, even with no servers being added or removed. So, for example, one of the things we were hoping to do, we had a customer years ago, online gambling called Betfair, and I actually used to work there. That's where I met you, isn't it?
Yes. That's where we went. We need this. We need to shard.
So, but we didn't steal him away from Betfair. We stole him away from this next business he worked at.
That was a financial company. Yeah.
So anyway, at Betfair, the interesting problem they had is that half of the load on the site, which turns out to be like something like billions of pages an hour. I mean, the number is just obscene, and most of it's robots, right? Because it's built like billions of pages an hour or something. I mean, the numbers are just off the scale. But half of the load on the site was against one atomic piece of data.
One object.
One object. So think about sharding, right? The goal of sharding, think of it like a deck of cards, right? If I have 5 people at the table and I'm dealing out the deck of cards, it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's like really easy, and then the deck's gone. That's like sharding, right? But what if everyone's interested in one card, right? What if everyone comes and talks to the person who has the ace of spades, right? Everyone, right? So I have 10 players now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, right? Everyone's still coming to the ace of spades.
Does it even matter about?
I could have 1,000 servers, and it's not going to be any better. So one of the when we started designing how we could augment the default partitioning approach that we used in our coherence product, one of the goals we had was to be able to push away partitions. So you could imagine a case where you have, let's say we did it as a heat map. in the Betfair case, they would have had one white hot, red hot, white hot, pick a color.
Pretty hot.
One very, very, very hot shard and a whole bunch of very, very dark blue, freezing cold shards, right? So you would want to leave that white hot shard wherever it is. Don't move it because it's got like everything coming. Don't move that, but slowly peel off all those blue ones from those servers. Send them somewhere else. Make it so that one server owns the primary copy of the white hot shard, one server owns the backup copy, and stick everything else on the other servers, right? So you dedicate 2 servers for one object.
And for a long time, their thought was we should move the hot one to another server, like a server that wasn't doing much. Let's move the hot one. And it's actually the worst thing to do. Like you've got all this hot data, moving it's going to cost you, right? We have to move it across the wire or some infrastructure. So leave it there and move all the others because they're like have a low SLA. And this is what we've been doing is experimenting because there is no like every use case is slightly different. So what are the permutations? And we're like,
oh, there you go.
So we actually can do this. It's like we can move partitions, shards manually, but we also want to be able to, this shortly starts to show heat as well.
So it's actually in this demo.
Yeah, it's in this demo. So you can start to see they become hot. And
those are the hot ones, the red ones?
Yeah. So we start to identify. Now, in the past, we were just looking at, making sure we have the right amount of data. But we realize, if you can actually design a system, have perfect shard, allocation, and still lose servers. Like a denial of service attack will take a server out. And so in the worst case, this degenerate case, we have one super hot object, which is atomic. You cannot cut the ace of spades up. Everyone has to queue up on that. There is no other solution. So you start to worry less about it. But so my other question was, what's the number of how many? Just think of time. We're over time, aren't we? We should have finished.
We are.
We're over time.
We haven't
How many shards should we have? You can answer.
Well, actually,
How does it go against the philosophy of the design time? Don't think about allocation.
Yeah, that's exactly right. Yeah, we in coherence.
What I'm hearing now is the other way around.
Well, at some point you have to go. You have to actually get it into a data center. You're going to deploy it, but when you write your code,
Deploy and watch it sometimes.
so
yes.
the model we're moving to is that everything is sharded.
Everything.
Absolutely.
Every single thing
Because
is
it turns
sharded.
out that the only thing that actually works in a distributed environment is a definite partitioning approach, either for availability or for scalability or for things like reliable, knowing the right answer to a question. So how many shards? The model, I don't know, maybe I shouldn't explain all of our detailed strategy for the long term, but the model that we're using is that there's actually different sets of shards.
Yes.
So in the first set of shards is what we call basically the configuration, the bootstrap, which is a single shard. Now, why would you do a single shard? Well, because you build, the key for high quality software is send everything through the same code path, right? You don't want like 10 different ways to do something. So by having a single shard approach, you can still have the high availability by having multiple copies and having, everyone knows to go to that shard. But now you don't care which server starts up first. Anyone here use WebLogic ever? WebLogic? Yeah, what's the first thing? If you're managing a cluster, what do you have to do? You have to start the admin server, right? And then it starts the managed service, right? Well, in the future, there shouldn't be that at all, right? You just start up servers. Doesn't matter which one starts first. It owns that initial bootstrap configuration, right? So that's the shard of one. So as the other servers start up, they know to get configuration from that. It's a partitioned configuration, if you will, but it's a partition of one. So everyone goes the same place, right? But then what is inside that bootstrap is the information about the next layer of sharding.
Rounds of sharding.
Is it services? Is it information?
So if you one way to also we're working from the bottom up, but we're also I'm working from the top down. Pick parts of Java EE. Pick part of the upper stack in terms of like SOA. Pick JMS. Pick HTTP sessions. Pick WebSockets. all of those you can apply sharding to, and when you do, you get this amazing ability to an elasticity built in, and that's the direction that we're heading.
And in fact, what you'll see for the reference implementations for Java EE that Oracle is responsible for in Java EE, we'll be introducing these concepts. So the reference implementations will all be shards of one, so to speak. But it's so that we can start to bake into the APIs of our products and in the standards themselves these concepts as basically fundamental building blocks. So for every service that we introduce in Java EE, it'll be built from the ground up to be running on 1 to 1,000 servers. So, and by the way, not 1 to 1,000 servers that you have to know about, but 1 to 1,000 servers that hopefully within a few years you don't even know how many it is, other than the fact that Amazon gives you a big bill at the end of the month.
Yeah, so you download your GlassFish feature, app server feature, or container feature, and you run it on your notebook or your desktop, and it's got one shard. And you sort of, okay, now I want to run it in a clustered environment with many. So okay, you just turn up the number of shards, and off it goes. So everything is just transparent. You should be able to then deploy to the cloud. You can develop with that technology and that metaphor. And we've been working on this for some time.
So what's live objects?
So last year we did a demonstration on a thing called live objects. You could take a regular Java object, annotate it, throw it in a grid. We demonstrate it with coherence, and it was exactly what we did previously. These live objects sat there, event driven. You can talk to them, you can invoke requests on them, you can kill the server and they just appear somewhere else. So it's just like this object that's alive compared to like a regular Java object, which should be dead. Stateful, handles events, can move around.
So that's the boulder.
The boulder.
Both rolling and standing still at the same time.
And we gave that presentation like 3 times, and the number one request was, can we get it into Java EE? And so we were, okay, so now we've got other research projects, and we started to think, well, let's bring along the Java metaphor. So we started to talk about elastic beans. So you want to define a Java bean, and hey, I want this thing to be elastic, and I want it to be grouped with these other ones, and just look after it. Container, look after it for me. And then when you move to cloud, like all of those abilities that you wanted, like we'll just do that for you. We'll just have that there.
Cool.
Sorry for running over a little bit, but thanks for staying. Oh, very nice.